Okay, so we are going to do chapter 3, matter and energy. And today in this chapter, I'm going to show you how to draw the mind maps. Okay, now here you will see that let's cover first thing first, the details. So first of all, what is a matter? A matter is anything that has mass. It's a material that makes up things. A matter is anything that has mass and it occupies space. Mass is, that means you can take the weight. Occupying space means it has a volume. So all these are different types of matter: pure substances, mixtures, elements, compounds, homogeneous substances, heterogeneous substances. Okay. Now, here's the thing, the pure substances. Pure substances have a very fixed composition. In other words, pure substances are made up of only one type of particle. Mixtures are made up of two or more different types of particles. Okay. Now, let's look at more. Here, the pure substance. Aluminum. Aluminum is made up of only one type of particles, just like copper, silver, gold. Here, a pure substances, only one type of particles. So these guys are pure substances. These, the ones that are made up of only one type of particles, these are called elements. And these elements, the smallest particles, which retains the physical and the chemical properties, that is called the atom. So for example, copper, the brown color, a solid, shines, conducts electricity, conducts heat, right? Can be made into wires, can be flattened into thin sheets. So all these are the properties of copper element. And when you take scissors and you break that element, that long piece, let's say a long wire of copper, and break it into small, tiny parts that still retain the physical and the chemical properties, that is called the atom, the smallest particle. That is the atom. The atom defines an element, okay? And we will study about atom, but an atom defines the elements, okay? Compounds, on the other hand, are made up of two or more substances chemically combined together. So for example, here, hydrogen peroxide. Here, 2 atoms of hydrogen and 2 atoms of oxygen are combined in a very definite ratio. So the smallest particle is called the molecule. So the compounds are made by chemical reactions. Elements are natural, come from God. Some of them we have synthesized in the lab, very few, but majority of them are found by the nature, very pure, how the earth was evolved. So it's nature, natural. But compounds, you can take the elements, you can combine them in a very definite ratio, and they can give you the compounds. Okay. Now, so 2 or more substances. Now, every compound also has a very specific property. Hydrogen peroxide is made up of 2 atoms of hydrogen and 1 atom of oxygen. Sorry, 2 atoms of oxygen to 2:2 ratio. Now, if you drink hydrogen peroxide, that's going to make you very sick. But H2O is made up of 2 atoms of hydrogen and only 1 of oxygen. So then it becomes the H2O is 2:1. That's going to make you healthy and hydrated, right? So a different property. So always a chemical combination, when they combine in a very, a definite chemical ratio, they produce molecules which have very specific properties. Table salt, for example. Now, sodium is highly flammable. It catches fire. Chlorine is brown, is greenish, yellow, a very toxic gas. So this toxic gas sodium and this toxic gas chlorine, and when these two combine together in a ratio 1:1, they produce table salt, which is healthy, right? We all need it for our food and those things. So that's the thing. Sugar, made up of carbon, hydrogen, and oxygen. Carbon is solid black charcoal. Hydrogen is a gas you cannot see. Oxygen is a gas you cannot see. But when these atoms are chemically combined, right, 12:22:11, in this ratio, only then they are going to produce sugar. Right? So that's the thing with all these chemical combination producing molecules. Okay. Now here, like I was talking to you about, sodium, very toxic solid, very toxic solid, and it catches fire. Chlorine is a greenish yellow gas. So when this gas and a solid combine together, that gives you a white colored table salt, a totally new properties. It is not a gas, sodium chloride, the table salt, right? But if you take the table salt, you will have to break it up into two parts by some chemical method. Table salt is not going to break into sodium and chlorine easily, as a chlorine gas easily, or a sodium salt easily. It has to go through some kind of a chemical process to break it. Okay. Next is the separation of mixtures. Simple mixture can be separated by very simple means. Okay, very simple means are the 1 second. Very simple means. Okay, mixtures are separated by very simple means, and those simple means are this is a process in labs we often use, and this is filtration. Okay, so basically this guy is just filtering. So this is a stand, this is a beaker, this is a funnel, this is a round, round like a ring, and inside it, this white thing is a filter paper. A cone. This filter paper has been made into a cone. Now this guy is separating a solid mixture. Solid mixture. I mean, it's a mixture of liquid and a solid. Now what happens is solid gets trapped in the what do you call the filter paper, and the liquid gets filtered. So the liquid comes here, the solid remains here. So this process is a very simple method of separation of a mixture. Okay, so different, no matter what, different two or more different substances, whatever their proportions are, it doesn't matter. But physical methods are simple methods where you can separate the mixtures. Now, here two types of mixtures. One is the homogeneous mixture, the other is a heterogeneous mixture. Homogeneous mixtures look the same. Now, here is a brass. Brass is a mixture of copper and zinc. But if you look also as sugar and salt, they mix together, they give you, so sugar and salt mixed together, and they give you like a mixture. It looks the same. So homogeneous mixtures are all one. But here is a mixture of oxygen and nitrogen gases, heliox, oxygen and helium gases, oxygen, helium, and nitrogen. So all these mixtures, sometimes they look as one. So air is a mixture of different gases. They are all one. They all look the one, so we can't see it. But we cannot see like the individual components separately. But nonetheless, they can separate them by not very complicated chemical reactions. But homogeneous mixtures, these, like I said, are made up of two or more different substances which can easily be seen by the naked eye. So this is a mixture of copper, metal, and water. And you can clearly see copper pennies sitting at the bottom and water floating on the top. So you can clearly say that this is a mixture, okay? Now here we talked about all these things, about the elements, compounds, homogeneous and the heterogeneous mixtures. So these are the basic things. Now, if you have, let's identify this. Pasta and a tomato sauce, what kind of mixture is this? Or even if it's a mixture or a pure substances, you tell me. Pasta and a tomato sauce. Is it a pure substance or is it a mixture? Write down the answer. Mixture. Very good. And what type of mixture is that? Pasta and tomato sauce? What type of mixture? Heterogeneous. Very good. Heterogeneous. Okay. Aluminum foil. Mixture or a compound or a pure substance? Aluminum foil. Aluminum foil is made up of only one type of particles. It's a pure substance. Okay, aluminum foil is a pure substance. It's made up of only one type of particles, and those particles are called atoms. Helium is a gas. What is it? It's a mixture or a pure substance? Helium, pure substance, because helium is not mixed with anything else, and this is helium is just a gas by itself. Air, mixture or a pure substance? Air. Air is a mixture of gases. Excellent, guys. Very good. Okay, so that's one thing. So this type of questions are going to be asked, Now identify which one is a pure substance, which one is a homogeneous or a heterogeneous mixture. Hot fudge sundae, homogeneous or a heterogeneous mixture. So it's like an ice cream with some kind of a cream topping, and it's like, I don't know what. So it is like a heterogeneous mixture. Okay, let's look at the shampoo. Shampoo. Shampoo is also a mixture of different things, but it's a homogeneous mixture. It all looks one. It's shiny, but depends also what kind of shampoo. But generally, shampoos are like that nice flow. So it's a homogeneous mixture. Sugar water. Sugar water. All one, right? Sweet water. It's all one. Okay. Peach pie. Peaches and in a pie, right? You can see the peaches. So heterogeneous mixture. Okay. So here's these type of questions are going to be asked, okay, on the exam. Now let's look at another one now. So hold on. All right. Let me get another one now. Where's the, okay. Next is state the properties of matter. Okay. Can you guys see? Let me see if I can get it this way. Hold on. One thing, I just want to make sure I can show you. Yeah. Now you see the screen? Do you guys see the screen? The states and properties of matter? Okay, thank you, Marissa, and thank you. Thank you, guys. So sweet of you. Thank you. Okay, now let's look at the states and properties of matter. Now here you see, it's a very interesting photograph here. This is, what is this here? What is this here? What is it there in the picture? Salt. Very good. It's a salt forming. This is like if you go, like Hayward, where that bridge is, what is it called? The San Mateo Bridge, that big one. So on one side there is salt forming. They do salt forming. You can miss it if you look towards, when you're coming from the San Mateo and entering into Hayward, from that side, when you see on the right hand side, the moment it's like when you're about to exit the freeway, right there on the right hand side, there's a huge land where they're doing salt farming. So you see this commonly. This is seawater. It gets trapped, and the seawater is trapped. And then what is happening here? How do you get the salt? How did they get the salt from the seawater? What did they do? What process is this? The process is, yes, evaporation. Very good. So through the process of evaporation, the heat from the sun, heats the water, and slowly the water evaporates. And what do we get? We get these salt deposits. Salt is dissolved in water, and it crashes out the moment the water evaporates, the moment the water leaves. And so we'll see a lot of these salt, like salts on the bed of this farms, we call them. And then later on, we collect the salt, we purify it, and then we market it, and so forth. So this is how the salt is collected. Very simple method of evaporation. Okay, seawater. Now, the salt contains sodium chloride. Okay, now that salt is sodium chloride actually. So the properties of the solid is of the salt is it's white in color, it is crystalline, right? And it is solid. It is made up of sodium and chlorine combined chemically in a very specific ratio, 1:1. All right. Salt can dissolve in water, right? So it has a very high boiling point. So even when it's in the salt and in the food, it's not like the salt is melting, it is just dissolved, right? So these are the properties of salt. So same is the case when we talk about the matter. There are three states of matter: solid, liquid, and gas. Okay, so solids, all of them have a very definite shape. This is a solid of a quartz, and the quartz is silicon dioxide. Very chemically combined silica with oxygen. Okay, a definite shape and a definite volume, a very definite volume, specific amount of volume. Particles are close together in a fixed arrangement. Okay, and the particles move very slowly. The particles are in this solid, they are just vibrating. Okay, they're just vibration, that's all. So they have a very specific shape. Solids have a very specific shape and a volume. The particles are arranged in that, specific order. Besides that, the particles are so close because the attraction in the particle is very strong. Okay. Liquids, on the other hand, the particles are loosely arranged. The particles, the attraction in the particles is not very strong. So which gives the liquids, they do not have a definite shape, but they take the shape of a container. You put the liquid, same amount of liquid, in a container, in a jar, or in a cup, or in a glass, or in a wine mug, or whatever, then it takes the shape of that container. So, but liquids have definite volume, but their shape is uncertain. But they're indefinite shape, but the volume can be definite. Okay. Now, these particles, because they are not very like bound to each other, there's a very weak attraction, so they are mobile. And this is the reason why the liquids flow. Okay. Then comes the gases. The attraction in the particle is the least, is minimum. There's no attraction technically. So these particles are very far away. Besides that, in gases, the particles are always randomly moving, always in constant random motion. The kinetic energy of the particles is very high. In solids, the kinetic energy of the particles is very low. In liquids, the kinetic energy of the particles is like in between. That is why they are able to move. But gases, the kinetic energy of the particles is extremely high. So because of this high kinetic energy, what happens? That these particles are always in constant random motion. They love to expand. You put the gas particles in the balloon. For sometimes they will remain inside the balloon, but then they find an escape route and they escape and they spread out into the air outside. So no definite shape, no definite volume. They will take the shape of the container. You take a gas, you can put it in a balloon, you can put it in different shapes of balloon, you can put them in containers like cylinders, you can put them in tubes, you can put them in glass rods. So gas particles, they can be, you can compress the gas particles and force them to be put in some kind of a container, like I said, cylinder. Okay. So that's the story with the gases. So that's the table, of course. And so this is, again, questions can be asked about these like the solid, liquids, and gases, their properties. So which is a general thing. Now, physical properties. Physical properties are the properties which are defined by our senses. What are the senses? What are the five senses we have? What are the five senses that we have? Yeah. Sight, right? Seeing, touch, hearing, right? Tasting, feeling, touching, and hearing, and then what else is smelling. Okay. So these are all the five. We define our world. Our world is defined by these five senses. Okay. Now, these five senses are basically they define how we see the world. But here's something you have to keep in mind. Just because we cannot see something, it doesn't mean it doesn't exist. It's present in the world. It is always there. So our world is confined because of the senses, but then matter has got it's got like so many different modalities to it, right? But the main ones for us here is definite. It will have some kind of the substance that we can, when we look at a substance, we can look at it and we can define by the color, by the smell, by the taste, by hearing. If you drop it on the floor, does it make a ting 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 sound, or does it make a thud kind of a sound? You see that? So those things are two different sounds, and we can clearly say when a ball falls on a floor, then we can, so it's a ball, sound of a ball. Even with the closed eyes we can tell. But if, like, say, something metallic form falls on the floor, like a, let's say, a spoon, ting 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 ting, or a steel, like a utensil or a plate, ting 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 ting, that sound. So we can say, like, okay, it's that particular object may have fallen on the floor, right? So those things we define, using our senses. So that's one piece. Besides that, we can also get the physical properties of the substances by seeing at what temperature does it boil, at what temperature does it freeze, right? Boiling is going from a liquid to a gaseous state, and freezing is going from a solid to a liquid state. No, so from a freezing is from a solid freeze, liquid to a solid state. Okay, boiling is liquid to a gas state. But at what temperature is that happening? Every substance has a very specific temperature when that transformation occurs. Density, how heavy the substance is. Is it lighter than water or heavier than water? Okay, what is the color of the substance? Besides that, there are other things also. Does the substance conduct electricity? Does it conduct heat? Can you make it into thin wires? Can you beat it into thin sheets? Right? So those things. Is it heavier than water or lighter than water? Will it float or will it sink? Okay, so those are the will it dissolve in water or is it not going to be soluble in water? Physical properties, all those are physical properties. Okay, so for example, here copper, right? You say copper is solid, brown color, shiny, made into some kind of objects by beating into thin sheets. It can be made into thin sheets. It can be made into wires. It can be stretched so much. If you stretch it, it can be made into wire. Right? It's an excellent conductor of heat and electricity. And at room temperature, it is solid. But when you heat it at 1083 degrees Celsius, it begins to melt. This solid begins to convert to a liquid. Now, if you keep on heating, the liquid copper will boil off, will convert from a liquid copper to a gaseous copper at 2567 degrees Celsius. Okay, so that's the boiling point. So that's the main thing with the physical properties. Now comes the physical change. As we talked about, physical change is a very simple change. Like evaporation is one method, physically separating things. Filtration is one method. Hand picking, removing things by hand. Sifting, by hand. And distillation is another one. But anytime a physical change occurs, no new substance is formed. It's a temporary change. Okay, the identity of those substances which are making that substance remains the same. So here we have water, we have solid, sand, salt mixed together. When they are mixed together in seawater, because seawater has so many other things, also impurities, but let's say main thing, seawater, if seawater was pure, clean, only clean, like clean seawater will have water and salt, but mixed together. Salt, although we cannot see, but it's a homogeneous mixture. And so we know water, certain properties of water, we know certain properties of the salt. So you can, when you separate them, the water remains water, the salt remains salt. So when they went in and made a solution of salt and water, they were the same, like that the chemical composition of the two, those two substances did not change. So let's look at some of the examples of physical change. Boiling of water, dissolving of sugar, taking copper, breaking up, making into thin wires. So just temporarily changing the shape. Cutting paper into thin pieces. So it still remains a paper, right? You take pepper, you ground it into thin flakes. It still remains pepper flakes, but it's a physical change, okay? Now you tell me, if you take a wood and break it up into small parts, is it a physical change or a chemical change? And as a change of state or a change of shape? Is it a change of state or a change of state? Chopping of log into kindling wood. Chopping. Chopping is, so it's just changing the shape, right? Water boiling in a pot, changing the shape or changing the state. Water boiling is changing the state. Very good. Going from a liquid to a gaseous state. Ice cream melting, change of state or change of shape? Melting of ice. Yes, state. Ice forming in a freezer, state or shape? State, right? Liquid to a solid. Cutting dough into strips. Very good. Shape. Okay, very good. Now, so we discussed that. Now let's look at the chemical properties. Thank you guys for participating. Thank you. Okay, now we are going to look at the chemical properties. Okay, describe the ability of a substance to interact with other substances to change with the new substance. So chemical properties are the substance are the properties that define the ability of a substance. Is this even going to react or not? Not everything reacts with each other, but that is the chemical behavior, the chemical property of that substance. Okay, just give me 1 minute here. Okay, next is the changing, and always a new substance is formed. So whenever a chemical change occurs, the original substance loses its identity. All the properties of the original substances are lost. And what do we see here? Here you see, when we make a cake or sugar, let's say sugar, this is a caramelized cake or whatever, it is a caramelized sugar. So you take sugar, you just put it on a pan and it becomes a brown sugar. And then it's a new thing, a new property, a new substance is formed. So you cannot go back and get the eggs out of it. You cannot go back and get the sugar out of it. You cannot get the flour. You cannot get the water out of it, or even the baking soda. So all this is this cake, a new substance is formed. Okay. Now, examples of a new substance. So let's say, look at it here. Classify each of the ice melts in the sun. Physical or a chemical? So these type of questions will be on the test. Physical or chemical? Ice melting in sun. Melt. Melting is always a physical property. Okay. Copper is a shiny metal. Physical or chemical? Physical. Very good. Next is the paper. Paper can burn. Is it a physical or a chemical property? Burning is always chemical. Okay. Silver nice can tarnish. Tarnish is just like rusting. Okay. Rusting, just like you create like an iron begins to rust. Similarly, silver and copper, they can tarnish. Okay. They can also react with like the oxygen in the air. Okay. A magnet removes iron particles from a mixture. Physical or chemical? Physical, because you're just removing. So it's not a chemical, it's a physical property. Okay. It's just a physical, you're just removing. Okay. All right, so again, these type of questions will be asked, all this, so you can just look at some of the more examples, but we need to move now. Let's look at the next thing now is the temperature. Now, here is an example of is it just all right. Now, temperature, let me make this big. Where is it? Okay. All right. So as you can see here, the temperature is a device. It is like an apparatus, which temperature that measures the degree of hotness in the body. Okay. To measure how much of the heat is present inside the body. That's the temperature. Okay. Now, here we see the temperature is This is a thermometer, degrees Celsius and Fahrenheit, degree Fahrenheit. So we have these two, units, degree Celsius and Fahrenheit. So here's the thing, for the water to boil, generally in the past we were using degree Celsius. We thought everything is in relationship to water, that everything freezes at 0 and boils at 100, something in that range, that thing. So we thought the maximum you could go is at 100, but later on they found out no, things can boil at like 2000, 3000, 4000, 10,000 degrees Celsius also. So now we had these scales, these thermometers with lots of markings, and all that, long thermometers we had to make. So it wasn't very efficient. Then we came up with degree Fahrenheit. Degree Fahrenheit and Celsius, it's the same. It's just the difference is that in degree, the range, it's the range of that, okay? So for us, for example, our normal average temperature in human beings, it's 37, 36, 37 degrees Celsius. But in Fahrenheit, it is 98, 96 to 98. It is a normal rate. Average human being should have a body temperature of 96, somewhere from 96.8 to 98.6. That's normal. Anything that's higher than that, 100, 100 to 104, that is like a lot. That is a high fever. 105 is like hyperthermia. Hyperthermia is hyper. Hyper is more. Thermia relates to heat. And then anything higher than that will obviously cause death. Hypothermia is lower. Hypo is lower. Thermia is again temperature. So below 96 degrees Celsius. So people can die of hypothermia also. Okay, either way. So this is our normal range in degree Fahrenheit. Now, here's the different temperature scales. It's the difference between the boiling and the freezing of water. So Celsius, it's 100 degrees, but in Fahrenheit, they made it 180 degrees. So here you will see the three thermometers. So here we have the water, boiling water, right? So water freezes at 0 and at 100 it boils. In Fahrenheit, the water boils in 212 degree Fahrenheit, and the freezing point of water is 32. So just the variation is about 180. But Kelvin is even higher. Kelvin goes very high and very low also. Remember that 0 degrees Celsius, below 0, negative numbers start, right? And then, so we wanted to give like more variations here. So 0 degrees Celsius, where the water freezes in Celsius at 0 degree, but in Kelvin, the water is freezing at 273. The water is boiling at 373. So the variation is still of 100 Kelvin, okay? So the three. Now, here's the thing. In your handout, I've given you the formulas. In your handout, if you look at the handout, I have the formulas of converting degree Celsius to Fahrenheit and Fahrenheit to Celsius. And we will look into that in a minute. So converting between, let's say this one is what? Okay, let's see. Where is the study check? What is the temperature which freezes water? Water freezes at, what is the temperature at which water freezes? 0 degrees Celsius. What is the temperature at which water boils? 373 K, right? How many Celsius units are between boiling and freezing of water? So it's 100 in the case of Celsius, in the Celsius unit. 180 is in the Fahrenheit, and 273 is the Kelvin scale, okay? So that's something, you have to keep in mind. Converting between the Celsius and Fahrenheit. So it's a difference of 1.8 degree Fahrenheit, basically. 1 Celsius is equal to 1.8 degree Fahrenheit. So this is like there. But like I said, I've given you the formulas. The formulas is right here. If you are given something in Celsius, a temperature in Celsius, multiply it by 1.8 and then add 32. Use the PEMDAS method. So multiplication first and then addition. So multiply whatever is given to you. So here we are given adjusting the freezing. So yeah, so we are given, let's say so this is one formula. Another formula is if you are given Fahrenheit and you need to convert to Celsius, then you take the Fahrenheit, you subtract 32 and then divide by 1.8. Okay, so these two are again given on your, this is again, the whole thing, it's not, we have already covered it, but just to tell you, like, the boiling different, all these different, like nitrogen in Kelvin, liquefying at -346 or 210 Celsius, those things. Okay. So these are just, we can do these problems. 1 second. Okay. And then the Kelvin. Kelvin, you take the Celsius, you add 273 to it, it becomes Kelvin. So, okay. So these are the units for these are the conversions. So let's do this now. I'm going to stop here and we are going to start okay, here, and I'm going to share my screen now. Okay. Okay. All right, so let's do this chapter 3. So a little bit, so basically the focus here is all going to be more on energy now. Okay, energy. Let's finish the energy part first. So I'm going to just thermometer, let's change it. Temperature. They changed the, oh God, 1 second. So we are going to do the problems that relate to temperature. And then we are going to look at the energy. All right, let's do that first. Okay, now for the temperature, let's look at the, let me open this. So where is the, oh, okay. So here you see the, no, right here. Okay, so this is in your handout, these formulas. So if you are given Celsius, you need to convert to Fahrenheit. This is the formula you will use. Fahrenheit to Celsius, this is the formula. And Kelvin, if you need, you're given the Celsius, you can convert the Celsius to Fahrenheit. Okay, so let's do this first, a few examples here. We will see, let us say, first of all, you are given something in degrees Celsius and you need to convert it into Fahrenheit. Okay, let us say degree Fahrenheit. Let us say you are given 36 degrees Celsius. And the question is, how many degree Fahrenheit are you going to get? So the way I'm showing you now, you will, on the exam, you have to always write the formula. I don't care where the formula is written, whether I'm providing you or whether I am, 1 second. Okay, whether I'm providing you or not, but you are always going to write down the formula, even if it's given in your handout. All right, here we go. So always write the formula. So we are converting degree Celsius. That means this is given to you as degree Celsius, and you need to convert it into Fahrenheit. So the formula then becomes TF, write this down, TF is equal to 1.8. 1.8 times the value of T degree Celsius plus 32. Okay, so here we have now TF is equal to 1.8 multiplied by 36 degrees Celsius. So you always solve this first. So I'm going to just, take away the 36 degrees Celsius. We'll just put the numbers. And then here, so do this first and then add 32. So we will have to follow the rule of PEMDAS. Please excuse my dear Aunt Sally. So this stands for subtraction. This stands for addition. This stands for division, right? Or fractions, and the fractions and division. This stands for multiplication. This is the exponent, and P is this is the exponent. This is the exponent. And then P stands for the parenthesis, something that is in parenthesis. So you always solve that first. So 1.8 times 36. Let's do this. .8 times 36. So here you get 64. Okay, 64. This is 64.8 plus 32. Now, before we even further, let's do this. So here you see is the two significant figures. Okay. This is just, we don't count the other ones. Now, you get 1.8 times 36, and that gives you 64.8. So in the steps, do not round up or down just because you want to have two significant figures. You leave it as it is. Okay, so 64.8 plus 32, and here you get 96.8. Okay, now here's the thing. This is one place after the decimal. Whenever we are doing the addition, then it becomes, so this is one decimal place. So your answer, final answer, should have one decimal place. In this case, do not round up, just so because you want to get the two significant figures, so leave the answer as is, leave as is. Okay, so within the steps, do not round up. Within the steps, do not round up. So always leave as it is. So whatever answer you get, you write down, it's 64.8, right? And then you add 32. Now here in the final answer, so this is the final answer. This is the temperature in Fahrenheit. So always write down the units. Okay, so always write number one formula, always. Otherwise, I'll have to deduct points. And second thing is the units. Okay, and show all steps, even though it's a simple problems, even though you're using the scientific calculator to do all the calculations. Doesn't matter. These things. So this is a very important thing. Otherwise, your points will be deducted. So keep this in mind. That's why I'm showing you. Points will be deducted. How did you get the answer? You could have guessed. Multiple choice. That's why we need to see these things. Okay, so that's one piece. Next, let's look at the next example. If you're given something in Fahrenheit and you need to convert it into degrees Celsius. So let us say you are given 36. Let's do this also. 36 degree Fahrenheit, and you need to convert. How many degree Celsius is that? So the formula for that is, the formula is TF degree Fahrenheit is equal to, okay, is equal to the degree, so how many Celsius is that? Sorry. So this is going to be, sorry, degree Celsius is equal to the degree Fahrenheit that is given to you, right? Minus 32, do that first, and then divide by this whole thing, because this is the whole thing. The way this formula is written, it's divide by 1.8. Okay? Right? So that's one thing. So now what you're going to do is you are going to put the 36 minus 32 divide by 1.8. So 36 minus 32 is 36 minus 32 is equal to 4. 4 divided by 1.8. And you get 2.22. 2.22. So here, basically 2.2. Now here's, keep this in mind. If this is the two significant, oh, sorry. This is two significant figures. This is two significant figures. Okay. So we need to keep these two and drop this off. Okay. So what do you get? The answer then becomes, the answer is TC is equal to 2.2 degree Fahrenheit. All right. So that's the thing, you know, with these conversions. And then you're going to do a lot of those conversions where Celsius is given to you, and you will be needing to do the conversion using the degree Celsius. 273 is added to it, and that's going to give you the Kelvin. Okay. All right. Next, look at now the concept regarding the energy. So on the exam, I want all these. Okay, guys, I want these. So,
excuse me, Professor.
yes.
I think the answer is in degrees Celsius, not Fahrenheit.
Oh, yes. You're right about that. I was thinking. So degree Celsius, yes, you're right about that. Okay, degree Celsius, that's the answer. All right, guys. All right, now we are going to look at the energy. So the rest is just practice. Okay, now we are going to look at the energies. Now, in this energy, since we are here and I don't want to waste this page, let's do this also. If you are given, let's do a number with the, yeah, let's do this one. You are given, before we start the energies, I still want to do this. If you're given a degree Celsius and you need to convert to Kelvin. Now here, a simple one. You are given 62 degree Celsius, or let's do this, say 63, 36 only. It's all the same. 36, okay. Positive 36 degree Celsius. Okay, positive 36 degrees Celsius. Convert that to Kelvin. Okay, so here you're going to take 36 degrees Celsius, add 273 to it, and you're going to get 36 plus 273. 36 plus 273, and you're going to get 309 Kelvin. Now, here's the thing. With the Kelvin, we do not use a degree. Okay, so for some reason, I think it's more like a bigger thing. So do not put degree sign. Okay, the degree sign. Okay, so just leave it like Kelvin. So that's one thing. But on the other hand, if you have negative 36 degrees Celsius, how many Kelvin is that? So here, same rule, negative 36 degrees Celsius plus 273. So in this case, plus minus minus. So 273 minus 36, and this becomes 237K. Okay, so plus minus is minus, and the sign is always going to be of the big number. So here this is subtracted. Clear? All right, guys. All right, next is we are going to look at the concept of energy. Now, what are the different types of energies that you guys know of? What are the different types of energies? Or what is energy? How do you define energy? Yeah. So here we are going to look at, first of all, the different types of energies, just so you are aware. Then we are going to look at the units of energies, right? Then we're going to look at the, and then the conversion of the units, conversions between the units. So it's just easy for you. Okay, next we are looking at the energy and nutrition. So energy and nutrition. How do you define energy in the terms of nutrition? So this is those people who are going to become dietitians, those things. So nutrition. Okay, next is the energy and nutrition, and then comes the specific heat. Okay, now that is also a concept of, the specific heat is also a concept of, it's also a physical property of a substances, and then calculating the specific heat, all those calculations that relate to specific heat. Okay, calculations. So more like Chem 1A stuff. Then comes the change of state. Okay, then comes the change of state, and here we will have, in this case, the change of state, we will have two things. One is the heat of fusion, and the next is the heat of vaporization. So those things we will discuss. Okay, vaporization, heat of vaporization. Then comes the evaporation, boiling, condensation, those things. Okay, though all that is coming from this, the change of state transformations. Next, we are looking at the curves, the heating and the cooling curve. So there's a lot here. Heating and cooling curve. Cooling curve. Okay, and then the next thing is that the combining the energy calculations, so energies, so combining energy calculations, energy calculations. Okay, so this is what we are doing. Okay, all right, so I think let's do one thing, because this is like a separate kind of a section. I want to create a separate video for it. So I'll stop recording this one, and then we will start like a fresh video on energy.